All right, so we're going to continue our discussion and move on to kinetic theory. And what we want to know is the relationship between pressure, volume, and an average velocity. Okay? Through that relationship, we can then find a relationship with kinetic energy of a molecule. Okay? So thermal energy, or the average translational kinetic energy of a molecule, is then going to be equal to 3/2 kT. Okay? And we can then solve for average speed of molecules, and that is going to be called VRMS. Okay? And that's going to equal to square root of 3 times K times T divided by M, our mass. Okay? Okay, so let's use that information and do an example. So this is example 13.10, and it states what is the average kinetic energy of a gas molecule at 20 degrees Celsius, or room temperature. Okay? So we can go ahead and use this formula that we just found. Kinetic energy equals 3/2 K times T, and plug in our values. So K is 1.38 times 10 to the negative 23 joules per Kelvin, and our temperature is 20 degrees Celsius, but again we need to make that into our SI units, okay, into Kelvin. So our kinetic energy then, our average kinetic energy, that's what this bar means in this case, is 6.07 times 10 to the negative 21 joules. Okay, so that's the average kinetic energy of a gas molecule at room temp. Okay, now it asks to find the RMS speed of a nitrogen molecule at this temperature. Okay, so the first thing we need to do is figure out what my mass is of that nitrogen molecule. Okay, so if you haven't taken chemistry yet, this might be a little bit confusing, but my mass is going to be my nitrogen mass, so 14.0. It's going to be times 10 to the negative 3 kilograms per mole. Okay, divided by 6.02 times 10 to the 23rd per mole, molecules per mole. Okay, so let me go ahead and explain what I just did. So this is my molar mass, and this is from periodic table. You can find that online. Okay, I'm not sure that it's in your book. It might be though. And then you divide it by your number of atoms per mole. Okay, or Avogadro's number, N sub A. Okay, and this will give you your mass. Now, in this case, we have 2 nitrogen molecules. See how it says N sub 2? So we need to also multiply that by 2. So whatever our mass is, we're going to have to multiply by 2. Okay, and we get a mass of 4.65 times 10 to the negative 26 kilograms. Okay, so this is our mass of our nitrogen molecule, and we wanted to know our VRMS, which is 3 kT over M square rooted. Okay, so we can plug that in. Remember our K is 1.38 times 10 to negative 23 joules per Kelvin. Our temperature is up here. 20 plus 273 is 293 Kelvin. Divided by our mass, I'm just going to put m, that's what this number is, and take the square root. And plugging all of that into your calculator, you will get 511 meters per second. So this is going to be the speed of that nitrogen molecule at room temperature. Okay? All right, so let's do another example, and it's going to be similar. It states, in order to escape Earth's gravity, an object near the top of the atmosphere at an altitude of 100 kilometers must travel away from Earth at 11.1 kilometers per second. Okay? This speed is called the escape velocity, since it's the speed that we are trying to escape the gravity. Okay? At what temperature would helium atoms have an RNS speed equal to the escape velocity? Okay, so remember VRMS is equal to 3 kT over m square rooted. Okay. And we're trying to find the temperature, so we can go ahead and use algebra to solve that. So it's going to be VRMS, and we'll need to square both sides. Okay, multiply by our mass, divide by 3 times K. So this is going to be our temperature, but we need to find our mass. Okay, so our mass of helium atoms will be, again, our molar mass. So 4.0 times 10 to the negative 3 kilograms per mole. Okay. And in periodic tables, your molar mass will typically be in grams per mole, but we can just get it in kilograms by saying, okay, in 1 kilogram, there are 1,000 grams. And so that's where we get that 10 to the negative 3 kilograms per mole. Just to tell you guys that real quick. I didn't mention it in the last example. Okay, so this is what we are looking at. Okay, so we have 4.0 times 10 to the negative 3 kilograms per mole. And we're going to divide by Avogadro's number, which is 6.02 times 10 to the 23rd per mole. And we get a mass of 6.64 times 10 to the negative 27 kilograms. Okay. So our VRMS is going to be, or I'm sorry, we're solving for temperature this time. Temperature is going to be my VRMS, which we're saying is the same as our escape velocity of Earth. And we want to put this into meters. So remember, there are 1,000 meters in 1 kilometer. Okay, so I'm going to put times 10 to the 3rd meters per second, and this is going to be squared. Okay, multiplied by my mass. Okay, and then divided by 3 times K. That should be a negative 23rd joules per Kelvin. And after plugging all of that into our calculator, we're going to get 1.98 times 10 to the 4th Kelvin. So this is the temperature that helium atoms would need to be to reach that escape velocity. Okay. All right, moving on to an idea called phase changes. Now we've got 3 different phases. Okay, I think I mentioned this in the last module. We have solids, liquids, and gases. We also have plasmas, but we're not really going to talk about that. Okay, so in order to describe the differences between these phases, so these are phases, we have a diagram called a pressure volume diagram. We also have these things called phase diagrams, which is PT diagrams, which is graph of pressure versus temperature. So these two. This one is much more common, I believe, in order to describe what's going on, what temperature and pressure you need to reach in order to be at these different phases. Okay, so looking at this diagram here, or this graph, this is going to be a PT diagram. Okay. We have these different areas at which these substances are at these different phases. So you can see there's a liquid phase, there's a solid phase, and a vapor phase or gas. Okay. And at some point there is a critical temperature, there is a critical pressure. And these are going to be where liquids can't exist. We also have a couple of other ideas called the triple point, where all 3 phases will exist in equilibrium. Okay. We have, okay, here's our critical point here. Okay. We have sublimation, which is a phase change from solid to gas. So these are just some ideas that I wanted to throw out there for you guys to understand. But really, I just want you to understand where our solids, our liquids, and our vapors will exist. Okay, this will be on your lab. You'll look at one of these in PhET. Okay. All right, so a bit more on equilibrium and such. Liquid and gas phases are in equilibrium at boiling temperature. Okay, so that's one thing to note. So if we go back, the liquid and the vapor are in equilibrium at boiling temperature. So boiling temperature is 100 degrees Celsius. So that must be around here. Okay, so this is where we have equilibrium between liquid and gas. We have a couple of different kinds of pressures. One called a vapor pressure, which is a pressure at which a gas coexists with a solid or liquid phase. Okay, so vapor pressure. We have partial pressure, where a gas would create, if it occupied the total volume available, that'll be its partial pressure. Okay, so vapor pressure would be somewhere in here or in here. Okay, then I wanted to mention Dalton's law of partial pressures. In a mixture of gases, the total pressure is the sum of partial pressure of the component gases, assuming ideal gas behavior and no chemical reactions between these components. Okay? All right. So I'm going to move on to this section in the next video.